everyone. My name is Ali and I am a final year PhD candidate in a drones lab at the University at Buffalo. I will present our paper titled EdgeSLAM Edge Assisted Visual Simultaneous Localization and Mapping. This is a joint work with Zakiya Sadat Hashimi Far and my advisor Kartik Dantu. Modern mobile devices are capable of complex computation, sensing, connectivity, and interaction. These capabilities have enabled lots of spatial applications such as digital manufacturing, which integrates digital design, simulation, and analysis to support product manufacturing and maintenance. Mobile interactive games on smartphones like Pokemon Go. Service robots, in which robots are used to perform several assistive tasks such as hotel room service. Augmented reality headsets such as HoloLens and Magic Leap that allow for collaboration where a group of people can visualize, share, and work on a common content in real time. Underlying these applications is the need for spatial sensing to perform essential tasks such as place recognition, localization, or path planning. There are several methods to perform spatial sensing. In indoor environments where GPS does not work, cameras and depth sensors can be used to obtain spatial information such as location. One method to obtain such sensing, and that is being used in many modern toolkits such as ARCore and ARKit, is visual simultaneous localization and mapping. Broadly, EdgeSLAM is a spatial sensing algorithm to map the environment and localize the camera in a global coordinate system. EdgeSLAM has been researched heavily in robotics as well as computer vision communities. There are several open source projects that perform EdgeSLAM, including RGBD-SLAM, RTAP-MAP, VINS, and OrbSLAM2. Typically, a EdgeSLAM system consists of three main modules: tracking, local mapping, and loop closing. These modules work simultaneously on a shared global map. The tracking module in EdgeSLAM processes the incoming camera frames. It detects features such as sift, surf, and orb, and matches the features in the current frame with the reference frame. If there is a significant change, the current frame will be assigned as a keyframe. The local mapping module processes the newly created keyframes. It adds the current keyframe to the map, optimizes the local map of that keyframe, and removes any redundant keyframes. The loop closing module tries to detect a loop whenever a new keyframe is added to the map. If a loop is detected, it closes the loop and performs a full optimization of the global map. EdgeSLAM systems have mainly been built for robots, autonomous vehicles, and not optimized for mobile devices. Running a EdgeSLAM system on a mobile device consumes a lot of resources, especially for long-term operation. The top graph shows the memory usage of OrbSLAM2 in a 30-minute run. The bottom graph shows the CPU usage over that time period. It is infeasible to let a service such as EdgeSLAM consume a larger fraction of the mobile device resources and limiting all other applications. One way to alleviate these resource constraints is using an edge server to offload some of the computation. In such architecture, the system could be split across a mobile device and an edge device to ease the resource requirements on the mobile device. However, one challenge in adopting the split architecture of edge computing is the tight coupling of the various modules in EdgeSLAM. Also, cameras produce images at 30 frames per second, which gives us about 33 milliseconds to process a single image frame. This limits the compute as well as communication latency when moving to the edge computing architecture, requiring a nuanced design to adapt EdgeSLAM to edge computing. In this study, we propose EdgeSLAM, in which we adapt EdgeSLAM to the edge computing architecture. Our primary focus in this work is to achieve three goals. First, reduce the amount of resources used on the mobile device. Second, to keep the resource use constant. Third, minimize the effect of such adaptation on overall localization and mapping accuracy. Shown in the lower figure, is our proposed architecture. It makes the following changes to the classic EdgeSLAM pipeline. First, we split the computing by running tracking on the mobile device and the local mapping as well as the loop closing modules on the edge. Second, we introduce local map, a data structure that resides on the mobile device that help mitigate the latency of tracking. Third, the edge server maintains the global map. And fourth, we introduce a two-way communication between the tracking module and the local mapping module to send the new keyframes to the edge, as well as local map updates to the mobile device. We base our EdgeSLAM implementation on OrbSLAM 2. OrbSLAM 2 is a state-of-the-art visual SLAM system for monocular, RGBD, and stereo cameras. The implementation is open sourced and consists of 20 classes and around 18,000 lines of code. OrbSLAM 2 operation depends on 3 threads, one per module, running simultaneously. There is also a fourth thread that runs on demand to optimize the global map. All 4 threads work on a shared global map structure managed through a complex locking mechanism, which demonstrates the tight coupling between the threads. A detailed breakdown of the logs and the way the data structures are shared between the modules is in the paper. Let us take a closer look at OrbSLAM 2. Once the tracking thread receives an image, it extracts all features. It then projects the local map into the frame to detect 3D map points. Finally, the features are compared to the reference frame to determine if this frame is different enough to be made a keyframe. A minimum number of features are required to maintain tracking. If this process does not yield enough features, it will switch to relocalization. When a new keyframe is created, it is passed to the local mapping thread for processing. In this thread, the new keyframe is added to the global map structure, and then a local optimization is performed. This optimization removes any redundant map points as well as keyframes, and optimizes the map data structure that is local to the new keyframe. For every new keyframe, the loop closing thread tries to detect a loop, that is, detect if it is back to a place it has previously visited. For this, it needs to compare its current keyframe with all existing keyframes in the map. If a loop is detected, then the loop is closed and optimized to distribute any pose error along the graph. The system then runs full bundle adjustment to optimize all keyframes and map points in the global map. This is a brief overview of the OrbSLAM 2 pipeline. More details are in the paper. Now we will discuss our EdgeSLAM implementation starting with the mobile device operation. On the mobile side, EdgeSLAM maintains a local map that corresponds to the map at the current location of the mobile device. In EdgeSLAM, the tracking thread runs on the mobile device and incorporates the following changes. First, the process of evaluating the current frame to decide whether to create a new keyframe is split across the mobile edge based on where each condition can be validated. In the new process, if the mobile side conditions hold for the current frame, a new keyframe is created and sent immediately to the edge for further processing. Second, when a local map update is received from the edge, the new map fully replaces the current local map, as discussed later. Third, if a tracking is lost, the mobile device tries to relocalize using the current local map. If not successful, it tries through an assistive map received from the edge. On the edge server, EdgeSLAM maintains the global map and runs local mapping, loop closing, and full bundle adjustment threads. We've made the following changes to local mapping thread. First, when a new keyframe is received from the tracking thread on the mobile device, the remaining conditions are evaluated to finalize the decision on whether to add the new keyframe to the global map or not. Second, a new module is added to the local mapping thread that is responsible for sending local map updates to the mobile device. The loop closing thread and full bundle adjustment thread in EdgeSLAM run as they do in OrbSLAM 2, since no significant changes have been made to them. Finally, the mobile device and the edge device communicate through separate network connections. An essential module to the correct operation of EdgeSLAM is the local map update module. Given that no optimization is performed on the mobile side of EdgeSLAM, receiving global map updates from the edge whenever there is a change is essential to prevent tracking error. However, this will also increase local map reconstruction overhead on the mobile device and network usage. Thus, our objectives for this module are to minimize the drift on the mobile device as well as reduce the cost of local map reconstruction on the mobile device and reduce the network usage. We accomplish this by sending frequent updates in short bursts. The updates are timer based and only sent if there is a global map change since the last update. Every update consists of the latest 6 keyframes and their map points. To evaluate our EdgeSLAM system, we use two distinct mobile devices and an edge device. The first mobile device is an NVIDIA Jetson TX2 that is comparable in specifications with Magic Leap 1. The second mobile device is a Dell Latitude laptop that is loosely comparable in specifications with Microsoft HoloLens. And the edge device is a Dell XPS desktop. We evaluate our system in different network conditions. The Jetson TX2 is connected to our lab private Wi-Fi network. The Dell laptop is connected to our campus public Wi-Fi network, and the Dell desktop is connected to our campus wired network. All these were run during normal working hours, with the Wi-Fi network experiencing representative load in a busy university building. We use a pre-collected RGBD dataset of campus building floor with around 52,000 frames and run for around 30 minutes for long-run experiments. We use a publicly available TUM RGBD dataset for short-run experiments. We perform 4 experiments. First, we run OrbSLAM 2 on Jetson TX2 and denote it in our figures by OrbSLAM 2 JTX2. Second, we run OrbSLAM 2 on Dell laptop and denote it by OrbSLAM 2L. Third, we run EdgeSLAM on Jetson TX2 as the mobile device and Dell desktop as the edge device and denote it by EdgeSLAM JTX2-D. Fourth, we run EdgeSLAM on Dell laptop as the mobile device and Dell desktop as the edge device and denote it by EdgeSLAM L-D. In the left figure, we compare the latency of each module in OrbSLAM 2 and EdgeSLAM. We observe that EdgeSLAM offloads the local mapping and loop closing modules, which are computationally intensive, and achieves a significant reduction in their latencies. Two things to note. First, in OrbSLAM 2, the local mapping and loop closing modules run on the mobile device, that is, Jetson TX2 and Dell laptop, while in EdgeSLAM they run on the edge device, that is, the Dell desktop, which has extra computing power. This is likely why those latencies are lower, and also why we offload. Second, the execution rate is different for each module. The tracking module is continuously executed to process incoming camera frames, while the local mapping module is executed whenever the tracking module creates a new keyframe. The loop closing module is partially executed for every new keyframe to check for a loop, and fully executed if a loop is detected. In the figure to the right, we show the latency for the tracking module, which is around 25 milliseconds on average. Given this module runs on the same devices in both systems, we observe no significant difference in the latencies. The two figures here show resource usage for OrbSLAM 2 and EdgeSLAM. The figure to the left shows the CPU load on mobile device running OrbSLAM 2 is between 25 to 40%. The CPU load to run EdgeSLAM is between 18 to 22%. This is an overall reduction of about 35 to 50% in computing load. The figure to the right compares the memory usage of EdgeSLAM with OrbSLAM 2. Our use of local map allows EdgeSLAM to keep the memory usage constant, while OrbSLAM 2 memory usage increases with a growing map. In 30 minutes, the memory usage of OrbSLAM 2 went from 5% to 20%, a four-fold increase. This slide shows that we have accomplished our first two objectives. That is, first, to keep resource usage on the mobile device low, and second, to keep resource usage on the mobile device constant. EdgeSLAM introduces latency and network overhead to send keyframes from the mobile device to the edge and map updates from the edge to the mobile device. We measured this overhead on multiple runs. The top table shows the overhead to create the local map update on the edge server, and the overhead to apply the map update on the mobile device. The most significant overhead is applying the local map update on the mobile device, which takes around 250 to 400 milliseconds. This is significant, but our empirical evidence shows that it is not detrimental to localization accuracy. The bottom table shows the overhead of transmitting keyframes from mobile to the edge. The latency to transmit a keyframe ranges from 140 to 160 milliseconds. Finally, we measure the accuracy of OrbSLAM 2 and EdgeSLAM and compare it to the ground truth. The top table shows the overall localization error. In all cases, OrbSLAM 2 and EdgeSLAM have a very similar error, about 20 cm with a deviation of 10 cm. Shown in the bottom figure are the 2D trajectories. Visually, there is minimal difference between EdgeSLAM and OrbSLAM 2. This slide shows that we achieved our third objective of maintaining accuracy in EdgeSLAM. We also perform additional measurements, such as relocalization latency, that are presented in the paper. To summarize, we presented EdgeSLAM, a way to modify VisualSLAM to offload compute using edge computing. Our code is open source and available at the link shown below, and I'm happy to take questions on our work. Thank you.